People have been telling me that living in Singapore, we are always under pressure. Now you are probably going to tell me that taking this course has given you a lot of pressure, from assignment after assignment, deadline after deadline. Well, this lecture is going to talk about pressure, but it is pressure in physical sense. So let's concentrate on the physical understanding of pressure. In physics, pressure is defined as force applied over an area where the force comes into contact. If I press my palm against a tabletop and put all my body weight on my palm, then the pressure that the table is experiencing will be my weight divided over the surface area of my palm. Please be mindful that it is the surface area of my palm, not the surface area of the tabletop, because my palm is not in contact with the whole tabletop. Pressure, denoted using capital letter P, which happens to be the same notation for power, by the way, is a scalar quantity. Its SI unit, as you could have guessed from the definition, is given by Newton per meter square, or Pascal, or PA in short form, named after a French mathematician cum philosopher, Blaise Pascal. Hence, 1 Pascal is the amount of pressure applied by a force of 1 Newton distributed over an area of 1 meter square. I don't think any of us in this class is a professional diver, but if you do dive recreationally, pressure is something you will definitely pay attention to. Pressure from surrounding open water is definitely affecting you. If you never dived in the open sea before, try to dive in the swimming pool. Soon you will experience your chest being crushed in by the outside pressure. Next, you will experience discomfort and sometimes, depending on person to person, pain on your eardrum because of the outside pressure pressing in. For that reason, there is a limit to the amount of depth you can dive into without any equipment. The question is, where does this pressure come from? Recall that pressure originates from force. When you dive to a certain depth, we denote this depth H. You are actually shouldering the weight of a water column that extends from the depth you are at all the way to the surface. Now that's a lot of water you have to withstand, by the way. Given the typical density of water, 1000 kg per meter cube, if let's say your bag has an area of about 1 meter square, that means at 1 meter depth, 1 meter cubic of water is pressing against your bag. That is equivalent to 1000 kg or 1 ton of water pressing your bag. Of course, I'm exaggerating here, but I hope you guys appreciate the enormous amount of pressure submarines or those deep ocean animals have to withstand at the depth they are operating. Mind you that seawater, because of its salt content, has a slightly higher density somewhere. Anyway, back to our main discussion. The pressure that you experience at certain depth comes from the weight of the water column above you. Dividing that weight by its cross-sectional area will result in the pressure at that particular depth. We know that weight is mass times gravitational acceleration, and mass can be written in terms of volume times density. The reason why we do this, so that we can recollect the volume at the numerator and the area at the denominator, and simply recast them in terms of depth h. We thus have the final equation, rho times h times g, which essentially tells us that the pressure from the surrounding water simply depends on the depth h. This equation is called hydrostatic pressure equation. The term hydrostatic refers to non-moving static fluid, which immediately tells us that the use of this equation is restricted only to situations involving still fluid body. If the fluid is moving, for instance if there is underwater current, then this equation is no longer applicable. In most situations, above the water surface there is already pressure. For instance, in this type of illustration, there is already atmospheric pressure at sea level. In this case, the pressure at depth h is given by the sum of the pressure at the surface and the hydrostatic pressure from the water column. This should be straightforward. Talking about atmospheric pressure, that is the pressure at sea level, it comes from the same principle, but this time around it is the pressure due to the weight of air column that extends from sea level all the way to the outermost layer of the atmosphere. Anybody know what this value is? It is 1 atm. Atm stands for atmosphere, and it is another unit of pressure, though it is not an SI unit. 1 atm is equal to about 100 thousandths or 10 to the power 5 Pascal. This is again an innermost number, because this means for every square meter on the ground, 10 tons of air are sitting on it. That is equivalent to the weight of a typical adult African tusk elephant. So that is one elephant sitting on you and me. Luckily, life is not so daunting for us. The reason why we do not feel as if an elephant was sitting on our chest is because the pressure inside and outside our chest is the same and they cancel off each other. Phew. There is also another assumption which I didn't point out earlier. In the previous derivation of hydrostatic pressure, we assume that the density rho of the fluid is constant over the depth h. Actually, this is not the case. The fluid is denser at greater depth, or similarly, the air is denser at lower altitude. The idea behind is similar to body piling, or in Singapore we call it taupok. Not a particularly safe game, but if you play this before, you would know that if you happen to be at the bottom of the pile, you would have to withstand the weight of everyone else on top. Similarly, the fluid at the bottom layer will have to withstand the weight of the fluid at the top layers. But this results in the fluid at the bottom undergoes compression and becomes denser than the fluid at the top layer. For that reason, you are breathing more air at the sea level than you are at, say, the top of Everest, 8,848 meters above sea level, where the pressure there is only 30% of that at sea level. The plot of atmospheric pressure versus altitude is presented here. This poses risk to the mountaineers who are not accustomed to operate at such low oxygen level, never mind the cold and gushing wind. Now, Blaise Pascal, the guy whose surname became the SI unit of pressure, decided to run the following experiment. He poured water down a long pipe. At the end of the pipe was a barrel, which was already filled up full with water. Pascal's experimental objective was to find out if pressure flows in certain direction. I mentioned just now that pressure is a scalar quantity, and hence it does not point in particular direction. But well, Pascal just wanted to be sure, I guess. As we would have expected, as Pascal continued pouring the water down, the water eventually burst through the barrel. Pascal then noted that the water sprouted out in all directions without any preference. This implied that the pressure was transmitted equally in all directions, or else you would see the water sprouting out on one side of the barrel but not on the other side. Thus he came up with what became known as Pascal principle. A change in pressure at any point in an enclosed fluid at rest is transmitted to all points in the fluid. In other words, pressure has no preference for direction. It is a scalar quantity and it applies homogeneously in all directions. This is the principle applied, for instance, in a hydraulic system. Examples of hydraulic systems such as hydraulic arm used in the crane or hydraulic jack are shown here. Whether it is an arm, jack or pump, the idea behind is the same. Using pressure to generate larger force, which can then be used to lift or pull heavy items from smaller force. Using hydraulic pump, such as the one shown in this picture, we can literally lift up a car using a hand pump. This is done by transmitting pressure from the smaller pump 1 to larger pump 2. Because of Pascal principle, such transmission is possible regardless of how pump 2 is connected to pump 1. And because the pressure in both pistons are the same, the ratio of force over area on both sides also has to be the same. The implication is that we only need to apply smaller force F1 onto smaller cross-sectional area of pump 1 to generate larger force F2 on the larger cross-sectional area pump 2. Now some of you may think that this sort of contraption doesn't make sense. You mean you can generate larger force from smaller force? Well, indeed you can. In fact, using smaller force to lift heavier stuff is not something new. In the last lecture, series 8, we just learned how to lift heavy objects with relatively smaller forces using a lever. Generating larger force from smaller force is not forbidden in physics. What is forbidden is generating larger energy from smaller energy. That is prohibited by the conservation law of energy. This hydraulic pump principle does not violate conservation of energy. The amount of work applied on the smaller pump, that is F1 times delta x1, assuming no loss of energy from friction or other non-conservative force, will all be converted into potential energy to lift the car up, which is mass of the car times g times delta x2 on the larger pump. Hence, the catch is, though we are able to lift an object much heavier than what normally your muscle alone can do, we are still required to push the pump longer just to lift the car a bit on the other side.